Every developer tackles multitasking differently. In this video, I'll show you a simple yet effective way to handle messages, one that you can use with confidence. A task is an independent part of a program, like a while loop. It should be structured as a state machine. All your tasks should be consistent for readability. To keep tasks consistent and allow those typedefs to have the same names but different content inside, use separate libraries for each one. Let's use a data acquisition task as an example. The main VI is in a project and inside the DAQ library. It has two typedefs, supporting its operation within a state machine paradigm. To allow our module to receive messages, let's define a message structure and establish a transmission mechanism. A message is a type-defined cluster. It contains a command, a type-defined enum containing commands we can send to our module, and command parameters, which can be another type-defined cluster for performance or a variant for flexibility. I find clusters more convenient. The key idea here is that when you define messages for a module, they are specifically tailored for that module to receive and process. Next, we define the sending mechanism. In most cases, a queue is the best choice. Now, let's modify the task so it can receive a message. The state machine architecture shapes the program flow. It typically starts with initialization, where you can define the message structure like this. Use the task name as a prefix for the message. Then, the task transitions to an idling state, periodically checking for messages. You can also add a checking message state. When a message arrives, the task reads the command and parameters, then decides what to do next. Remember to connect 0 to the timeout input. If no messages arrive, the state machine continues running as defined. To keep our diagram clean, let's encapsulate the messaging details within a component, a message handler, which is based on a functional global variable. Here, the variable stored in the shift register is a queue. Notice that functions like initialize communication, send message, and get message internally call lower-level functions such as create queue, dequeue, and enqueue. However, the names of these functions abstract away those lower-level details. Instead of exposing queue operations directly, we define a higher-level interface, making the communication method clearer and easier to use. This abstraction is what makes it an action engine. When the functions operate on a simple variable, like a counter or timer, the function names clearly describe actions on the shift register data, justifying the term functional global variable. But when the component defines higher-level actions, it becomes an action engine. At last, you can enclose those communication-related elements into a subfolder inside your task, so it looks like here. This way, we can build two tasks, data acquisition and user interface. Each task should be placed in its own library along with its communication definition. Each has its own program definition and initializes its own communication. Now, when we press the Start button, we want to send a start acquisition from user interface task to data acquisition task. So we transit to send start DAQ. Here you drag and drop data acquisition message handler and simply define the message. In data acquisition task, you read messages in checking message state. When start ACQ arrives, we get the information about number of samples, update this information in our program data, and transit to starting acquisition, where we start our task and transit to acquiring. Here we use the user interface message handler to pass the new data message back to the user interface. We can receive the data back, like this, in check status state. Summarizing, this technique requires some setup, but as you can see, it keeps the structure clean, maintainable, and easy to follow, giving you confidence in building a robust multitasking application. At last, put both tasks in your main VI, and that's it.